Okay, good morning, everyone. Today we will discuss the lecture still about the fluid flow. But before we continue the lecture, last week we have discussed about first is about the flow regime. Yeah, in the fluid flow, it's important to understand the phenomena of the flow in terms of flow regime. Basically, there are two extreme differences in flow regime. First, what we call laminar flow. Laminar flow is visualized by the upper picture. It's a very smooth flow occurred in very low velocity or flow rate, and there will be no mixing. So smooth flow means there will be layer by layer of fluid, and every layer have a same velocity profile in terms of this one. So in the middle, in the center of the pipe, the velocity will be maximum, and it will be decreased throughout the wall of the pipe, because throughout the wall of the pipe, the friction between each layers is getting higher. And in top layer or in bottom layer, which next to the wall, the friction will be maximum and there will be no velocity. That's the characteristic of laminar flow. The other extreme, we call it turbulent flow. It occurs in very high flow rate. There will be no keteraturan, yeah, there is no smooth line, but it will be the very oscillating motion around the pipe. And basically, when you have this kind of flow, turbulent flow, you may say that you will have similar velocity throughout the radial position. Jadi kecepatannya untuk aliran turbulen Anda bisa seragamkan. And you can calculate average velocity by calculating the volumetric flow rate divided by cross-section area. And to differentiate which kind of flow will be classified as laminar or turbulent, we use the parameter called Reynolds number. So Reynolds number, this is the basic equation of Reynolds number. So Reynolds number will be equals to density of the fluid times diameter of the pipe times linear velocity of the fluid and viscosity of the fluid. This is the basic equation of Reynolds number. And by definition, or the physical meaning of Reynolds number, it is the ratio between the inertial force divided by the viscous force. It has no unit, so you have to remember that when you do the calculation of Reynolds number, you have the similar types of units in each parameters. For example, you calculate in standard unit, for example, or in MKS unit, or you can use CGS unit, but it needs to be consistent for all the parameters. Then you will have the Reynolds number, which is the dimensionless number. And from this equation, density times diameters times velocity divided by viscosity, then you can use other parameters, like you convert mu over density is equal kinematic viscosity. And density times velocity will be equals fluid mass flux. This one, right? So this is the Reynolds number. The value of Reynolds number, how to differentiate the flow regime, you can use if the Reynolds number is less than 2000, it can classify as laminar. And if it is higher than 4000, then it can be classified as turbulence. Later, when we discuss about the pressure drop, we will discuss it further later. For laminar, it will be proportional. Pressure gradients mean delta P. It will be proportional to Q at the power of N. When the flow is laminar, N will be 1. And if the flow is really, really turbulent, then it will be 2. But in between, we call it transition, and the order, the power will be between 1 and 2. But for now, just remember that this is the boundary or the limit of each flow regime. Okay, from this concept, do you have any question before I continue the lecture? Okay, should be clear enough, right? Okay, and yesterday I have mentioned that others than to identify flow regime, actually later we will discuss the application of Reynolds number. Sorry, just a minute. Okay, others than determining the flow regime, you can use later the Reynolds number to determine the friction factor, and then to determine the friction loss in the fitting, or to determine the drag coefficient. But we will discuss it in the later chapter. Okay. Just remember again that Reynolds number will be influenced by, diameters. And this is the diameter of the pipe. But you need to be careful with the phenomena when the fluid flowing through the pipe. Okay, for example, if you have a cylinder pipe, then you have gas flowing through the pipe. Yeah, if you have gas flowing through the pipe, gas will be fully filling the pipe, right? However, if you have liquid flowing through the pipe, it will have different phenomena depending on how much or how big the flow rate. For example, if you have very high flow rate of the liquid, then it will be also fully fill the pipe. But sometimes, if the liquid is very low, the velocity or the flow rate is very low, then it's only filled some parts of the pipe. Okay, so if you have fluid that are not fully filling the cross section of the pipe, then you need to be careful when putting the value of the diameter in Reynolds number, because actually this diameter will be influenced by this phenomena. Okay, so it will be some differences in how to calculate diameters when liquid is flowing through the pipe. But for the gas, it's okay because gas is always fully filling the cross section, right, during the fluid flow. But for the liquid, sometimes it will be fully filling, but sometimes it's only partially filling. That's why you need to determine perimeter. Perimeters is actually length of the cross section of the pipe which is in contact with the fluid. So only part of the cross section that's contact with the fluid. So for example, in the left circle, so the perimeter will be the whole circumference. Keliling apa sih? Circumference ya. So for the liquid that fully filling the pipe, the perimeters will be the whole circumference of the pipe. But if the fluid is only filling part of the cross section, then the perimeter is only this one. Is the diameter of the pipe different? No, there will be no differences in the diameter of the pipe. But there will be differences in putting the value of D in Reynolds number. How to calculate the value of D in Reynolds number? You need to determine first the perimeters. Okay, after you know the perimeters, for example, like this one, right? So for the left figures, the perimeters will be this one. And for the right figures, the perimeters will be this one. Yang ini, this one, is not the perimeters. Then, if you have liquid that's not fully filling the pipe, then there will be diameters equivalent or equivalent diameters. Or sometimes you call it hydraulic diameters. And how to calculate the hydraulic diameters or equivalent diameters? Diameters hydraulic will be 4 times radius hydraulic. So it's different between the concept, the first that you know that D is 2 times R, right? So if you calculate the hydraulic diameters, it will be 4 times hydraulic radius. And radius hydraulic or hydraulic radius is the cross-section area divided by the perimeters or the weighted perimeters. So for the left figures, area will be whole circle sectional area. And the perimeters will be the circumference. So for this one, A will be equals if you know the diameters, then A will be, what is the formula to calculate cross-section area?
Pi r square, sir.
If you, in terms of D, it's this one, right?
4 pi d. 1/4 pi d. Okay.
And how about the circumference? Sorry, not the circumference. How about the weighted parameters? Weighted parameters will be this one. And this one will be equals circumference. So weighted parameters will be P times D. Kelilingnya kan P kali D ya. So for this one, the diameter equivalent will be 4 times using this formula. This one equals P. That's why if the liquid is fully filling the cross-section of the pipe, the hydraulic or the equivalent diameter will equals to the pipe diameters. But for this one, it's different. You need to know the value of the cross-sectional area first. This is the cross-sectional area. And then you also need to calculate the weighted parameters.
Sir?
Yep.
For the weighted perimeter, is it just the perimeter of the pipe, sir?
Not the whole. So you need to see which length. So weighted parameters, the unit will be length. Unit is length, but which length? Only the length that in contact with the liquid. That's why it's called weighted parameters.
Okay, sir, I got it, sir.
Okay. So for the case of the right figures, you need to know, for example, this is the half of the circle, then how high is this one? And then you can convert it into the cross-sectional area, and then you can calculate the weighted parameters. Okay, this is for still in the circular pipe, but the fluid, the liquid, is not fully filling the pipe. Or you may see the case like this one. So the liquid will travel through the pipe, but the cross-sectional is rectangular. It's like a water what? The talang air at home. So in the first case, the pipe cross-sectional is fully rectangular. So it has a side at the bottom and also close at the top. Same in the case 2, but in the case 1, the water is not fully filling the pipe. But in the second case, it's fully filling the pipe. And in the third case, the water is also fully filling the pipe, but the pipe doesn't have enclosure at the top. So just remember that diameter equivalent will be 4 times RH, will be 4 times cross area of the liquid, not of the pipe. So this one is cross-sectional area of liquid divided by weighted parameters. So for the first case, the cross-sectional area will be this one only. This one. For the second case, the cross-sectional area is this one. And for the third, is the same.
Sir, the 4 there is part of the formula, right, sir?
Yes, if you calculate
Okay.
the you need to add 4 times radius hydraulic. Radius hydraulic is the cross area of liquid divided by weighted parameter. So equivalent diameter will be 4 times this one. And for the first case, the weighted parameters is only this one. Because it's only, that's the part of the cross-sectional area, cross-sectional of the pipe that have contact with the water. But for the second case, it will be this one. All the sides of the rectangular. And for the third case, is this one. Because even in the third case, the liquid is also fully filling the pipe, same like case 2, but the pipe doesn't have enclosure at the top. So there will be differences in calculating the equivalent diameters. Okay, any questions so far?
All good, sir.
Okay, so let's continue. How about this one? The left figure, it's called the annulus pipe. Annulus pipe is double concentric pipe. So it means there will be smaller pipe inside the bigger pipe with the same center. And then the water will be flowing inside the space between these two pipes. That's called annulus. Normally, you can find these types of arrangement in, we call it shell and tube heat exchanger. So you need to exchange the heat. The name is heat exchanger, right? So like cold fluid, you flow it to the annulus, and then the hot fluid, you flow it into the smaller, inside the smaller pipe. So for example, in this area, in this system, the water flowing in the annulus, this one. So the same, the hydraulic diameters will be 4 times area divided by the weighted parameters. So the area should be this area. It means it is the area of the bigger pipe, right? The cross-sectional area of the bigger pipe minus the cross-sectional area of the smaller pipe. That's the area. How about the weighted parameters? Weighted parameters will be all the length that have in contact with the water. So it means it will be the circumference of the small pipe plus the circumference of the bigger pipe. That's why the calculation will be this one. Or the diameter hydraulic or diameter equivalent will be bigger diameters minus smaller diameters. So you need to be careful about the phenomena of this liquid that flowing to the pipe. You need to determine how full the liquid filling the pipe, and then you need to determine or calculate the area. Area is area of the liquid, the cross-sectional area of the liquid, not the whole cross-sectional area of the pipe. So in this one is only area of liquid. And weighted parameters is the length that have in contact with liquid. Okay. Okay. Another thing that you need to be careful when you are using D in calculating the Reynolds numbers. You understand, right? If you see the actual pipe will have certain thickness, right? Yeah. So pipe will have certain thickness. So it will have value of inner diameters and the value of outer diameters. Which diameters that you need to use in calculating Reynolds number? Is it inner or is it outer?
The inner, sir.
The inner, correct. Because the liquid or the fluid will be flowing inside the pipe, right? So the calculation of Reynolds number will be based on the inner diameters. The problem is, in the real world, the pipe size is normally mentioned not directly in inner diameters. It will be mentioned, it will be stated as the nominal pipe size. For example, if you go to the toko bangunan and then you want to buy some pipe or some fitting, then the seller will ask which size. Sometimes you mention 1 in. In means inch, 1 in, or 3/4 inch, or half 1.5 in. This is called the nominal size of the pipe. The unit is inch, usually is in inch. Normally, for each nominal pipe size, for example, 1.5 inch, it will have different schedule number. So it is a standard number. We call it schedule number. Actually, it will represent the thickness of the pipe. The higher the schedule number, the thickness will be higher. So like this one, right? 40, schedule number 40 is 0.1, and schedule number 80 is 0.2. It means the inside diameters for the higher schedule number will be lower because it has the same outside diameters. So you need to be careful if the pipe size is stated as the nominal size. Usually it is stated like 1.5 schedule 40. Then how to determine the inside diameters? You need to have the table, this kind of table. From where you can get this kind of table? You can get from the handbook of mechanical engineering or chemical engineering. You can get these types of table. And you need to use the inside diameters for the Reynolds number. But again, do not use this number directly. You need to see how full the fluid filling the pipe. If it is fully filling, then you just need to use the inside diameter directly. But if it's not, then you need to calculate the equivalent diameters. I think should be clear enough, or do you have a question? So this table is also example of the data that you can get from the handbook. It's showing the nominal pipe size correlating with the schedule number and the from this one you see the difference, right? In this table you have the value of inside diameters directly. Then you can use this value unless you need to convert into diameter equivalent. But for this table, you only have the value of nominal pipe size, the schedule number, the outside diameters, and the wall thickness. Then inside diameters should be outside diameters minus 2 times thickness. Don't forget to do that calculation. It's easy, right? But sometimes when you are in exam, maybe because of the rush, then you forget the formula. So if you know the thickness and you know the outside diameters, don't forget to multiply the thickness by 2 to get the value of the inside diameters.
Sir,
Yep.
is this regarding from this table, sir?
What do you mean? Sorry.
We have to use this formula to find the inner diameter through this table, sir.
Yeah, because if you only have this table, you do not have the value of inside diameter directly, right? It's different from this table. This table, you got the value directly. If you know the nominal, you know the schedule number, then you have the inside diameter in the same table. But if you what you have is this kind of table, you only have the nominal outside and the schedule, then you only get the value of the thickness, right? Then how to get the inside diameters? It's like this one, right? So thickness is this one. This is outside, and this is inside. So it will be 2 times thickness, right?
Okay, I understand, sir.
That's why. Actually, this formula is actually by nature. Then from the figures, then you can calculate by using this formula. But sometimes students are in a rush, then they forget to do this. Like the inside diameters is only outside diameters minus thickness. We forget that thickness is at the upper part and also in the bottom part. Okay. Okay, the right tables actually is showing that the schedule numbers are how do you say it? It's different, depends on the materials of the pipe. So like for carbon steel or wrought iron, depending on the ISMA, ISMA is the standard of the materials. Then it will have like from 5 into 160 schedule number. But for the stainless steel, it's like 10s, 40s is just the standard. Again, you need to have the data like in the table. Then you need to get the value of the inside diameters. The basic formula to calculate the schedule numbers, but we rarely use it in our lecture. So in the schedule number is like 1000 times pressure divided by the stress. But you don't need to consider this formula. It's just for your information. Okay. Do you have any question? Not, then we go to the mass balance. I think your NMA class is already have the mass balance equation, right? So in flowing fluid, the mass conservation law is also followed. It's also used, which stated that mass can either be created or destroyed, and then the mass of the product in the chemical reaction must equal the mass of the reactant if the conversion is 100%, of course, and then the mass only can change from one form into the others. Okay, that's the basic principle of mass balance. Can I ask you what is the general equation of mass balance? Accumulation rate will be equals to
something to do with regeneration and degeneration.
yes, something to do with that. Neracanya sudah sampai sini belum? Persamaan umum neraca massa.
Udah, sir.
So
Tapi,
the rate of mass accumulation rate will be rate of mass in or inflow minus rate of mass outflow, right?
plus generation
Correct. Rate of mass generated.
minus consumption, sir.
Okay. Rate of mass consumption. That's the general equation of every mass balance. Okay, in this flowing fluid, you just imagine liquid, water, for example, flowing inside the pipe. There will be no rate of generation and rate of consumption, right? Because it only comes from the reaction. Correct, right? So for the flowing fluid only without any reaction, then there will be no mass generation, no mass consumption. And then in the flowing fluid, we can encounter or we can have what we call steady state condition. What is steady state condition? What is the
State
meaning?
in which the factors are not affected by time, sir.
Yes, the parameters is not changing by time. In this one, the mass flow, the mass rate, I mean. So this one, for the steady state condition, there will be no accumulation of mass. So in the simple flowing fluid in the pipe, there is no reaction and steady state condition is achieved, then the rate of mass inflow will be the same of the rate of mass outflow. Inlet will be the same as outlet. Gampang kan ya? This is very simple for flowing fluid. Okay, we have the explanation in the next slide. So this is the general equation. Can be applied in any kind of system with or without reaction, steady or not steady. And then for the steady state, the rate of accumulation will be 0. And for the flowing fluid, there will be no reaction. So the mass generated and mass consumed is also 0. Then you have the flow rate of mass flowing into a system will be the same as the flowing flow rate, the same as the flow rate of the mass that flowing out of the system. Okay, simple, right? Okay. Okay, before we continue, then just a step back, then accumulation. You can call it dm over dt, right? Okay, this is the general accumulation. And then you always you remember that mass will be equals density times volume divided by dt. Correct, right? Density is this one, volume is this one. So mass. In the general equation or general case in the real world, the density and the volume of the flowing fluid will be changing along the axial length. Ya, jadi selama perjalannya along the travel of the fluid, along the flow of the fluid, maybe because of the changing of the pressure and also because of the changing of the temperature, the density will change. Hence, the volume will also change. So, actually, you can, it's from your calculus, right? So, you can expand this equation becomes this one. Okay. This is the general equation for the accumulation rate. If the fluid is considered compressible. Compressible means the density is changed. But if the, so this one the general equation, if there will be no accumulation, it will be equals 0. But for now, we considered first that the fluid is incompressible. So density is constant. So density times volume, because it's equals mass, right? It's constant. For now, later when we discuss, when later Pak Anggit will give lecture about the compressible fluid, then we will consider the changing of volume and density. Okay. Now for the steady state mass balance, the first that you need to from this equation, right? From the final equation from this one, you will have if the liquid are flowing from point 1 to point 2. So along the travel, along the flow, the mass flow rate will always constant. Laju alir masanya itu selalu konstan. That's why M1 equals M2 for the steady state. Steady state mass balance without reaction. Okay, mass is density times volume. And then volume will be equals to velocity times cross-sectional area. That's why you have this one. Okay, this is the equation of continuity. So basically, equation continuity equation is mass balance equation in steady state. So the mass flow rate will always same, is always constant along the flow. It's the continuum. It's always constant. So you derive from mass flow rate into the second term. And if the fluid is incompressible, it means the density is constant. Then you can take out the density. Then you can have this equation. Then, sorry, this one, oh, there is some mistakes. This one, U. Right? So this one will be equals this one will be equals this one. Linear velocity is meter per second times area square meters. It will be cubic meters per second. It is the called the bit or volumetric flow rate. So if the fluid are flowing in steady state condition and the fluid are incompressible, previously the mass flow rate is constant, but if the fluid is incompressible, then the volumetric flow rate is also constant. Ya. Jadi kalau fluidanya itu mengalir dalam kondisi tunak steady state, kemudian fluidanya itu incompressible, densitasnya tetap, maka yang tadinya laju alir massa kan tetap ya, ini juga bisa dianggap laju alir volumetriknya tetap. So the constant volumetric flow rate is only happen when the fluid is incompressible. Of course, it's always in the steady state condition.
Sir, I have a question, sir.
Yeah.
V sama U, what's the difference, sir?
It's the same. Okay. Disclaimer. Sometimes in this slide, U, sometimes small v, and sometimes even big V is changed. Sorry for not making the parameters
It's okay,
the same.
sir.
So you need to understand the meaning of the symbol. It means the linear velocity.
What about the one that you said volume is equal to velocity area, is it, sir? Is that right?
Which one? Which one?
Going back to the rho1 times v1 equals to rho2 times v2.
This one.
Yeah.
This is volume.
Yeah, the v is equal to u times a. That u is velocity, right, sir?
Yes. This one is velocity. This one. Hey, sorry. Oh, there is some mistake. This one is volumetric flow rate. Sorry. This is volumetric flow rate, not just volume. This one is key.
So it's the debit that you were talking about, right, sir?
Yep. Thank you for the correction.
Okay, thank you, sir. I got confused there with the units.
Okay.
Thank you very much, sir. So I'll change it to Q, okay, sir?
Yeah.
Sir, then how does it relate to mass again, sir? The density multiplied by Q. Is it still equals to M? Because
Flow rate.
M dot.
M dot is mass flow rate. It's kilogram per second. So this one should be, let's do the kilogram per cubic meters, right? Times cubic meters per second.
Okay, sir. I understand, sir.
So in this lecture, you need to always check with the unit. If the unit is the same, then the formula is correct. Any other question? Okay, then I will continue. This one you do not need to confuse with the equation and some symbol are missing. But if during the travel, the pipe is changing in terms of cross-sectional area, it means the size of the pipe is changing. It means the linear velocity will also changing, will also vary around the cross-sectional area. But you already understand that for the incompressible and steady state, that Q is constant, right? But only for incompressible. So if the Q is constant, but the cross-sectional area is changing, then you just can calculate at certain point of the pipe, linear velocity will be this one. Cross area. Okay, this one is cross area. Yeah, you just need to calculate the average velocity at certain point.
So the velocity along the pipe will be the same, right, sir?
Velocity is not. The volumetric flow rate along the pipe will be the same. The volumetric flow rate. But the velocity, the linear velocity will vary.
Okay, sir. And the area, you use the cross-sectional area, right, sir?
Yes, the area is the cross-sectional area. So it means the
Okay.
area of the circle.
Do we take account that one, sir? The cross-sectional area in which the fluid is in contact with the pipe, sir? Like just now, if it's not fully filled or something, sir?
Oh, yes, of course, yes. If the liquid is not fully filling the pipe, then the cross area is only the cross area of the liquid, not the full cross area of the pipe.
Okay, sir. Thank you very much.
Actually, later we will have the term superficial velocity. Actually, the same as this linear velocity. The unit is also meter over second, but this is a term to specify the area of the liquid, how full the liquid filling up the cross-section area of the pipe. But when you do the mass balance equation, of course, area will be cross-sectional area of the liquid if it's not fully filling the pipe. Good question. Ya, jadi Anda harus mempertimbangkan juga seberapa penuh. Kalau ini cairan ya, kalau gas kan nggak masalah. Kalau cairan kan ada kondisi dia tidak penuh mengisi pipa. Jadi perhitungan-perhitungan areanya itu area yang diisi oleh cairannya saja. Oke?
Sir, I have another question, sir.
Sure.
In the diagram, when it says x1 there and x2, what is it saying, sir?
Actually, this is the integration of the flow, but you don't need to consider it for not now. So it's just when you want to like takes. Remember when we discussed about the wall of the dam and we do the analysis of the force from the left and for the right, then we take small length, right? So actually this one is to see the changing of the area and the influence of the changing of the velocity, because when you're changing the area, the pressure will also changing, right? So like taking account in changing of the area, changing of the pressure, and then you correlate with the changing of the velocity. But for now, you don't need to confuse about this symbol. So just use the general equation that average velocity is Q divided by A. Oh, one more. sometimes you need to mention the flow rate in terms of flux. You still remember flux, right? Flux is mass flow rate divided by area. So the unit will be kilogram per second divided by square meters.
Sir, so here you would identify the m square divided by the cross-sectional area of where the pipe is, sir.
Sorry again?
So over here you would calculate the for example the volumetric first multiplied by the rho of the fluid. Then
Mhm.
the area would be which part do you want to calculate the flux in which area is it? So the
Yes,
cross-sectional area of the pipe or like the of the fluid lah. Yeah.
yes. So for example, if the mass flow rate will be constant, right? Everywhere the mass flow rate will be constant. Mass flow rate, the kilogram per second one. The volumetric flow rate, as long as the density is constant, the meter cubics over second will also the same. But if you mention it in terms of flux, when you divide it by area, so you need to see which area that you consider, whether this area or this area or this area. For example, the area will be different, right? So the mass flux, the mass flow rate divided by area will also different. So for the mass flux, it will not be constant throughout the pipe. Jadi yang konstan adalah laju alir massa. Itu pasti konstan. Mau kompresibel, mau incompressible, yang namanya laju alir massa pasti konstan. Ya, selama tadi ya steady state. Tidak ada reaksi juga. It's always constant. The mass flow rate will always constant. Okay, mass flow rate is always constant. As long as steady state and no reaction. Okay, the second one, if the fluid is constant, the density is constant, incompressible, mass flow rate is kilogram per second, the volumetric flow rate, cubic meter per second, is always constant. This one is only. But if the area are changing, for example, like the green figures on the right, so if the area are varied, then the linear velocity, the unit is meter per second, is also varied. Mass flux, kilogram per second over square meters, is also varied. Why it's varied? Because the mass flow rate is always constant, but the area is changing. So the mass flux is also varied. Okay. Any other question?
It's all good, sir.
Okay. If there is no other question, then the mass flow rate or the continuity equation, the constant mass flow rate, is also applied when the pipe is divided into several branches. For example, this one, at point 1, liquid are flowing inside, the fluid are flowing inside, and it will be divided into point 2 and point 3. So just remember that inlet mass flow rate will equals outlet mass flow rate. So you have this one. And then mass flow rate is density times volumetric flow rate. You have the second equation. Then if the density is constant, then you have the final equation. This one should be plus. Okay, so the changing in velocity, again, like the same, actually the same. If the area of A2 is similar area of A3, so the mass flow rate or the volumetric flow rate will be divided in half. Correct, right? If you have the same diameters at point 2 and point 3, then the mass flow rate or the volumetric flow rate will be divided in half. But if you have different area, then how? You need to calculate first.
Using
Yes.
ratio, sir.
Yeah, you can use the ratio, or you can use, or basically you need to calculate first the each area of the inlet and outlet, and then you can correlate with this formula. Okay.
Sir,
Yep.
for the previous one,
Mhm.
will the volumetric flow rate be the same for 2 and 3?
If the diameter is the same, yes. So if you have
Oh, okay, okay.
A1, sorry, A2 equals A3, then Q2 will be equals Q3 will be equals half of Q1, right? Because it's
Okay,
just
okay.
divided equally.
Okay, understood,
Same.
sir. Thank you.
M2 will be equals M3 will be equals M1. Only if the area is the same.
Okay, thank you, sir.
Okay. Okay. If there is no other question, let's do this example. But I need to make some correction again in terms of the numbers. So this one is Q2, this one is D3. So this one is 0.1, this one is 0.2, this one is 0.3. So the system is the tank. The tank is filled with water. The filling point is from point 1 and point 2. At point 1, the average velocity will be 5 meter per second. At point 2, the diameter is 50 millimeters, and the volumetric flow rate is 0.012. This is Q2. And at point 3, the diameter is 60 millimeters. And you need to calculate the value of velocity at point 2 and velocity at point 3. But there is some condition if the level in the tank remains constant. What does it mean?
Input equals to output, sir.
Yes, correct. So it means if you need to take the level of the tank remains constant, then will be this one. Or Q1 plus Q2 will be Q3. Okay, by using this assumption, or this is actually a steady state condition, right? Because there will be no accumulation in the tank. The head of the tank will be the same. So please calculate how much is velocity at point 2 and velocity at point 3. Okay, I give you 10 minutes, should be enough to calculate. Or do you still need some clarification about the exercise?
It's okay, sir.
Sudah selesai?
Udah sir.
Berapa ketemunya?
Yang U2-nya I got 0.24. Yang U3-nya I get 3.5. If that's right sir.
Coba diulang, sorry. 0.24
sama U3-nya 3.5.
kayaknya bukan deh. The value should be similar, not similar, but it's close to each other. How about others? Yang lain sudah selesai menghitung? So U2 is 0.24 at the top, right? So U2 is just key at 2, 0.012 divided by A2. A2 is
50.
Yes. But just remember it's in millimeters.
Oh my god, sir. Okay, I get my mistake. I just counted diameter and I didn't change it to area, sir.
Okay.
Oh my god.
So should be four. I think it's 4 times, right? Just be careful when you do the calculation.
All right, sir. And also 50 millimeters, change it to meters, right, sir?
Yes, should be all in the same unit.
Okay.
I mean, meters should be in meters because the diameter should be in meters because the flow rate is in the cubic meters per second.
Is it 0.3, sir, for U2?
0.3 should be 4 times. If you did not put a quarter, then it should be 4 times at the previous. Oh, no. Just calculate first. How? What is the number that you get?
So I did 0.012 divided by 1/4 times pi times 0.05.
0.0.
0.05, sir. Because you changed 50 millimeters to meters, right, sir? That's divided by 1,000.
Square, right? You take the square.
Oh yeah, I forget to take the square.
Come on, please be careful.
Is it 6.1, sir?
Yep, I think it's around 6. How about the others?
I got 6.12, sir.
Which one? Velocity at point which?
U2.
6.1.
6.1.
And then velocity at point 3?
Belum nyampe sana.
Okay, please do the calculation.
Is it 6.5, sir, for U3?
6.5. I think close to that. I forgot
Like
like 6.1 and 6.4, if I'm not mistaken.
6.46, sir. I get
Yeah.
6.46. That's why I rounded off to 6.5.
Okay, I think it's correct. It's around that value. How about the others? Do you have the same answer?
Sir, anyway, can I ask you something, sir?
Yes, sure.
Uh, have you uploaded like the previous class, sir?
It's in YouTube. I think I
Is it
already
YouTube? Oh, it's
upload.
already in YouTube, sir. Okay,
Yes,
okay. I haven't checked, sir. Okay, thank you very much, sir.
supposed to be in YouTube, but
Okay.
the last lecture is until Renault's number, right?
Yes, sir.
Hmm. Should be. Oh, not yet, not yet. I haven't uploaded to YouTube. I'm sorry.
It's okay, sir.
Okay, I think I skipped that one. I haven't uploaded it. Okay, I think I upload. I will try to upload today.
Okay, thank you very much, sir.
Okay. Oke, yang lain dapat angkanya apakah sama? If I'm not mistaken, it's around 6.1 and 6.4. Yeah, close to that.
Yes, sir.
Alisa also got the same number, so it should be correct. Okay, can we continue?
Yes, sir.
Okay,
Yes,
this
sir.
one, I'll give it to you as the homework. But actually, I will have another question for the homework until end of this part of the lecture. I already give to the regular class, but I haven't translated in English. So after I translate, then I will give to you all. But at this point, you have the value of each velocity, right? At point 1, at point 2, and at point 3. So now change the value of the velocity at point 2. Previously is 6.2, right? Or 6.1. changed into 8 meters per second. But the same velocity at point 1, which is 5, and this one is 6.46. But the velocity changed the value of velocity at point 2, and then please calculate the change of the water level. dH over dt is how much? By assuming that the diameters of the tank, this one is 1 meters, diameter of the tank. Should be straightforward, the calculation. Okay, I leave it to you as the homework. Okay, now we have another example. This one is the branch of the pipe. So we use the concept of the nominal pipe size. So you have the oil. Oh, sorry. Oil with the density of oil is 892 kilogram per cubic meters. Flowing to the point 1, and you will have at point 1 the diameters, the nominal diameters. This is not the inside, but its nominal diameters is 2 inch. Okay, flowing to the pipe with the total rate is 1.388 times to the power of minus 3 cubic meters per second. So it should be the volumetric flow rate. So total rate means the volumetric flow rate seeing from the unit. So if you are not sure what is the total rate, just see the unit. Entering at pipe 1, and then at pipe along the flow, at pipe 2, the pipe have higher diameters. But then after flowing at pipe 2, the pipe is divided into the same size of 1.5 inch pipe diameters. At pipe 2, the diameters, the nominal diameters will be 3 in. And all the pipe have schedule number of 40. Okay, now you need to calculate the following all in standard unit. The total mass flow rate. So the first one is total mass flow rate. Mass flow rate is always constant, right? In each segment of the pipe, except for the branch, because it will divide it in half. Okay, so you need to calculate mass flow rate, for example, at point 2, at point 1. How much? This is in kilogram per second. And then mass flow rate at point 3. How much? In kilogram per second. And then B, the average velocity. Average velocity is linear velocity at point 1 and at point 3. The unit will be meter per second. And then mass velocity. Mass velocity is kilogram per second per square meters. Okay, to solve this problem, you need what do you need to do first?
For A, I guess you have the density of oil, which is 892. Then after that, you have to find the Q, in which it is 1.388, right, sir?
Yes.
Then you can find the mass flow from there, sir.
Okay, mass flow is actually the density times Q. Correct. Then how about the mass flow rate at point 1 and point 2 is the same?
Yes. Then after that, when it goes to pipe 3, then you just divide it by 2, right, sir?
Right. So for the pipe 3, mass flow rate at pipe 3, it will be half mass flow rate at pipe 1. And then how about to calculate the velocity?
To calculate the velocity, since the formula of the Q is U times, okay, U is equal to Q divided by A, right, sir?
Yes. So you need the value of A. A will be influenced by the diameter of the pipe, right?
Yes.
Yeah. So you need to calculate, or you need to find out the value of the inside diameters, because it's
And
all still in the nominal diameters.
we have
Yes.
to search for it from the table, right, sir?
Yes. You need to get the table. After you get the value, then you just do the calculation.
And also the diameter is the diameter of the inner thickness, right, sir? So the outer diameter minus 2 times the thickness, is it, sir?
Depending on the table. If the table, from the table, if you already get the value of inside diameters, then you just use the value. But if
Okay, sir.
you only get the value of outside and the thickness, then outside minus 2 times thickness.
Okay, sir.
Okay. Then after you get the velocity, what will be one velocity at point 1, velocity at point 2, and velocity at point 3. Which one is the highest? Or which one is the lowest? Or if you compare the velocity at point 1 and point 2, which one is higher? So the volumetric flow rate is
It's
constant.
higher at 2, sir,
Higher at 2. Why?
because the area is smaller, sir.
Okay. Area at point 2 is higher than area at point 1, right? The pipe is bigger.
Oh, sorry, sir. Pipe 2-inch. I was looking at the 2-inch pipe, sir. Sorry,
Okay.
sir. Yeah.
Yeah. So at the segment number 2, the diameter is higher. So the velocity will be smaller compared to velocity at segment pipe number 1. Okay. And at point 3, then you need to calculate first at point. Actually, the velocity of point 3 will be half, not half of the velocity, right? So the for point B, key 3 will be equals half of key 2, right? I write down here. The mass volumetric flow rate at point 3 will be half of the point 2 because it's equally divided. Then to calculate, just do the same T3 divided by A3. To get the value of A3, you need to know the inside diameters. How about the flux mass velocity?
You have your M, then you just divide it by the area.
Yes, correct. Just this one. Mass flow rate at segment 1 divided by area at segment 1. Again, for the value of the area, you need the value of the diameters. You have the answer in the next slide, but I hope you can understand the way of calculation. Okay, don't forget to convert nominal diameters into inner diameters, and then you convert from inch into meters, because the unit of the nominal still in inch. Okay, any question?
Sir, so we have to remember the conversion unit, sir.
Yep. I think for
Like
length,
1 inch is 2.54 centimeters. So you have to
yes.
remember that. Okay.
I think for the simple conversion, you need to remember.
Okay. Sir, will we be given like from inches to feet?
Uh, but usually in the first modular exam, it's totally closed book. So for the simple conversion, like from feet to meters, inch to meters, uh, you need to remember. So if you want to convert inch to feet, then just do the step-by-step calculation.
Okay, sir. Thank you, sir.
Okay. I think for length, for temperature, and then I think it should be easy to remember, right? Okay, any question?
Sir, I have a question, sir.
Hmm.
How do you know that mass velocity is asking for flux, sir?
Oh, this is the term that already stated in the textbook. I took it from the Giancoplis. This is the Giancoplis. Giancoplis state the mass velocity as flux.
Okay, sir.
Okay. So the term like because different textbooks sometimes they use different terms.
Are there any more things that we should know that regards with flux, sir? Because like, yeah, it's just scared that it will pop out in the exam, sir.
Sorry, I cannot hear you clearly.
Will there be like any other terms that is regarding to flux, sir? Because like scared that it will pop out in the exam, sir.
But normally the standard term is flux. So in exam, if we ask about flux, then we will write it as flux. Flux is rate divided by area. Yeah, these GAN copies do not use standard term, so it's called like mass velocity. So maybe sometimes we will confuse whether it's asking about the mass flow rate or other terms velocity, right? But in exam, normally we will ask the unit as well. We will write down the unit as well.
Okay, sir. Thank you
So
very
from the
much.
unit, you can guess. Actually, it's asking about which one.
Okay, thank you, sir.
Okay. Any other question? Okay, maybe I'll continue a bit about the energy balance. So, beside mass balance, flowing fluid are also following the energy balance. It means the energy is also constant. It's not the energy is also constant. The total energy is always constant. Okay, but energy can be transformed from one form to another. Oke, neracanya sudah sampai neraca energi belum ya? Mungkin belum ya. Atau termonya sudah sampai neraca energi? Belum.
Kayaknya belum deh, sir.
Kok kayaknya? Okay, so just remember for now that the total energy for flowing fluid is always constant. The total, but the form can be transformed. So later we will discuss about what kind of energy contained by the flowing fluid. And to calculate the value of the energy or the energy level of the object or system, we use or it can be expressed, it can be calculated based on the relative energy. But later you will have this lecture in thermodynamics. So there will be certain datum or baseline to calculate energy in terms of relative energy. Ya, maksudnya gimana? Maksudnya adalah perhitungan energi itu biasanya sebagai it's not absolute energy, but we calculated the energy compared to the energy at certain position or a certain level. For example, later we will discuss. Okay, this one is the example of the energy contained by the flowing fluid. So basically, there are four types of energy that contained by the flowing fluid. First is the internal energy. Internal energy is the energy contained by the flowing fluids because the fluid has certain temperature. Yeah, because the fluid got certain temperature, then it carries certain amount of internal energy atau energi dalam. So internal energy will be calculated based on the temperature. The equation is mass times, do you know CV? Do you already got these parameters in thermodynamics? No?
Yes, sir, we got this already.
It's the heat capacity, right?
Yes,
Time,
sir.
temperature. Nah, temperature is compared from certain level of temperature to the temperature of the flowing fluid. Maksudnya tadi itu. Jadi pengukuran temperaturnya itu biasanya didasarkan antara beda temperatur. It based on the different temperature difference from the flowing fluid to the standard temperature. For example, 0 degrees C or room temperature. Okay. If during the flow, the fluid are isothermal, isothermal means T is constant, there is no change in temperature, then there is no change in internal energy. Okay. The second type is kinetic energy. This is the energy contained by the flowing fluid because the fluid got certain velocity. And the equation will be, I think you already remember, right? Half times mass times velocity to the power of 2. Okay. The third forms is potential energy. Potential energy contained by the fluid because the fluid got certain position compared to the baseline. Baseline means like ground level. So if the head is different, then the potential energy is different. Okay, and the last one is pressure energy. Pressure energy, by the name itself, is contained because the flowing fluid got pressure. It means the higher the pressure energy is higher. Like the kinetic energy, the higher the velocity, then the kinetic energy is also higher. So the energy will be pressure times volume, or pressure times mass divided by density.
Sir, what does the specific energy mean, sir? Does it
Later,
just mean like per unit of mass, sir?
Yes. Okay. This is the four types of energy of the flowing fluid. You see, what is the unit of the energy if you calculate using the Mohs column? Kalau Anda menghitung energi pakai rumus yang paling kanan, what will be the unit? Joule, right? The unit of energy, the standard one?
Yes, sir.
Joule. Okay, all still got the parameter of mass. So sometimes the energy can be expressed by the unit of energy divided by mass. That's called specific energy. So for the specific energy, the unit will be joule over kilograms, the standard. So you can express the energy in terms or in units of joule, the real energy, right? I mean, yeah, the energy, or as specific energy, the joule per kilograms. That's called specific energy. Specific means divided by the mass. Later, or maybe, I think previously we already discussed what you call specific volume, right? This is volume divided by mass, or inverse of density.
Yes, sir.
Yeah, this is called the specific volume, the volume divided by mass. Energy divided by mass called specific energy. Okay, any questions so far? So basically, there are 4 types of energy contained by the flowing fluid. For simplification, later we can neglect some parts or some types of energy. This is what we call ideal fluid. So ideal fluid, which is characterized by Bernoulli equation. So basically, Bernoulli equation is energy balance equation, but for ideal fluid. What is ideal? What is the assumption of the ideal fluid? First, it's steady state. Steady state means there is no accumulation of energy. The total of the energy will be the same. There is no energy accumulation, there is no energy loss, etc. And then the second one, no energy loss. The third one is isothermal. Isothermal means there is no change in internal energy. And then the fourth one is there is no input energy. Jadi tidak ada input energy to the system, and then there is no work done by the system. So this is the assumption of the Bernoulli. First is steady state. Actually, the second is isothermal, and then there is no energy loss, there is no input energy, there is no work done by the system. So for the Bernoulli, ideal Bernoulli equation, there are only 3 types of energy, which is pressure energy, potential energy, and kinetic energy. Okay, any question? Okay, so if there is no question, I think we should stop until here. And the replacement class tomorrow, I will give you the link for tomorrow. It will be different from the normal regular class. I will send you through WhatsApp. So tomorrow at 3 p.m., right?
Yes, sir. 3 to 4, sir.
Okay, thank you. See you tomorrow, and bye-bye.